The chronology of events that unfolded during the first half of the 20th century brought unparalleled achievements in our understanding of the mechanics of flight. From the basic structures of airframes and airfoils to the application of thermodynamics and mechanical power, we have seen the art and science of aeronautics moved forward at an exceptional pace. If we look back at the origins of these accomplishments, we learn they were often won at great cost, but also great reward. Our engineering history should be celebrated for its steadfast record of successes and failures that have advanced us to the current state of the art. In Part 2, we examine the accelerated pace of development of air power as it was influenced by the necessities of combat during the Second World War. Power and aircraft performance more than doubled in a few years' time. Today, in Part 3, we will examine the peak of development of internal combustion aero engines and then look at some of the early developments of turbojet power. Wright Aeronautical's successes in building the Cyclone series resulted in further development of twin-row radials to capitalize on their investment. The Wright R2600 twin Cyclone used 14 cylinders in 2 rows capable of 1,500 horsepower and eventually delivering 1,900 horsepower. To build an even higher powered engine, Wright conceived the R3350 in 1936 as an 18-cylinder twin-row, utilizing the same bore and stroke of the R2600, then completing type testing. Some of the design features were forged steel cylinders, Wright patented W-type cooling fins, sodium-cooled exhaust valves, and exhaust ports facing forward on the front row and aft on the rear row. The supercharger case was cast from magnesium. The story of the duplex Cyclone is closely tied to the top priority development of Boeing's B-29 Superfortress project. Although both were conceived before the U.S. was drawn into the conflict, as events unfolded, the need for a long-range heavy bomber quickly came to the top of the priority list. As proposals came into the Army, Wright's yet unrefined R3350 was the only engine of its size potentially available to airframe builders. By the time the initial order for the B-29 was drafted, only a few engines had been delivered to the Army for tests in a Douglas B-19 test bed. All tests had been accomplished at low altitudes and low power settings. Overnight, the demands upon Wright Aeronautical grew exponentially. Boeing's new super bomber encompassed quantum leaps in every aspect of its design. That the R3350 was going to be built and tested in an airplane being rushed into production begged for trouble. Fuel-air mixture distribution plagued the basic design early on. Oil system inadequacies required multiple revisions. Resulting engine fires when fed by magnesium components were catastrophic. Cylinder head design was initially compromised due to the insufficiency of the manufacturing capacity of forgings. As part of a massive effort to get the airplane operational, a system of production and subsequent modifications brought solutions to the multitude of problems with both airframe and power plant. Introduction into service carried many of the issues with it. Changes in tactics reduced some of the liabilities, including the eventual low-altitude employment of the B-29. Direct fuel injection, one of the solutions for the mixture problems, was partially successful and employed in the program. By the end of 1945, most of the R3350's issues were resolved. Late World War II designs using the more developed duplex Cyclone included the Lockheed 749 Constellation, P-2V Neptune, and Douglas Skyraider. Douglas' huge single-engine attack bomber combined roles of previous Navy bombers into a single multifunctional platform. The ability to carry more ordnance than a World War II B-17 demonstrated the potential unleashed by the Wright duplex Cyclone. The Skyraider's R3350-26W variant was rated at 2,700 horsepower with water injection. Douglas jack-of-all-trades could carry 320 gallons of internal fuel, augmented by external tanks or weapons under its wings. Service in the Korean War proved both the airframe and the engine in combat. Wright further developed the R3350 into the 1950s into what is considered the most capable and highly refined production piston engine ever built. Employing the concept of turbo compounding to return exhaust gas energy to the crankshaft, the late variants developed up to 3,700 horsepower with efficiencies previously unimagined. These powered the Douglas DC-7 and Lockheed 1049 Constellation to the end of the piston era for major air carriers. Other specialized uses of Wright's duplex Cyclone were yet to be imagined. Late in the war, the Reich's Air Ministry was reaching for alternatives for better high-altitude performance. Although it was in development before the war began, Daimler's DB603 had been temporarily discontinued in a decidedly short-sighted view of the future. The massive V12 was 44 liters, or 2,716 cubic inches. It featured Daimler-Benz standard hydraulically coupled supercharger, and development was restarted for use in the Messerschmitt Me-410, Heinkel HE-219 Night Fighter, Dornier Do-335 Heavy Fighter, and Focke-Wulf TA-152 Sea Fighter. Early AA variants were altitude rated with single-stage superchargers. The later DB603L, a two-stage, two-speed version under development, would provide 2,000 horsepower for takeoff, 1,850 horsepower at 27,000 feet with GM1 boost. When Kurt Tank proposed the V12-powered FW190, it was intended to use the DB603 from the outset. The annular radiator of the modular power unit featured a perpendicular flow through the radiator sections, guided by a smooth fairing aft of the propeller spinner. Viewing the underside of the engine module for the Heinkel 219, the Bosch direct fuel injection pump is visible in the space between the inverted V banks. A crew of 2 with a radar operator in the aft-facing seat was credited with 5 Lancaster bombers destroyed in the early morning hours of June 12, 1943, while the 219 was still under operational test. Dornier's massive twin-engine centerline thrust Do-335 Feel was Germany's fastest piston engine fighter of the war, powered by 2 DB603 engines. The rear engine behind the cockpit drove the aft propeller via an extension shaft, and a speed of 474 miles per hour was recorded under test by the Do-335. Early production versions were engaged in operational tests in May 1945. Focke-Wulf's last piston-powered fighters were extrapolations of the basic FW-190 series. The FW-190D9 entered production in late 1944 and nearly brought the performance to parity with the P-51s and Spitfires they contended with. Because the intended DB603 engine was not yet available, Kurt Tank proceeded with an interim design powered by the UMO 213A with single-stage two-speed supercharger. The UMO 213A was a redesign of the UMO 211F, designed from the outset for a pressurized coolant system and able to run at higher RPM. The UMO 213 displaced 35 liters and was rated for 1,750 horsepower at 3,200 RPM. The FW190D series was further developed with the two-stage, three-speed UMO 213E and F series engines. The FW190D13 was equipped with the UMO 213F, optimized for lower altitudes, and was rated at 2,022 horsepower at 3,250 RPM. While outwardly similar to the FW190D9, the more powerful UMO 213 promised significant performance boost and carried heavier armament. The 220mm cannon in the inboard wing was augmented by a 30mm Mark 103 motor cannon firing through the propeller hub. Limited production deliveries had begun in the spring of 1945 with this aircraft, delivered to the staff flight of JT-26 and flown by Group Commander Franz Getz. By contrast, the UMO 213E, installed in the TA-152H, employed an air-to-air intercooler as the charge left the second stage of supercharging to allow higher boost for better altitude performance. The TA-152H was flight tested to 47,000 feet, and a maximum speed of 472 miles per hour was attained at 41,000 feet using GM1 boost oxygen enrichment. A single survivor of this remarkable achievement sits disassembled in storage with the National Air and Space Museum. While Rolls-Royce had established the single-stage 1,000 horsepower Merlin II engine in production, Fleet Air Arm had expressed an interest in a larger V-12 for use in a new naval reconnaissance fighter, the Fairey Firefly. Based upon engineering experience gained from the Merlin, development proceeded smoothly with prototypes running in 1939. The larger 37-liter Griffin used the same bore and stroke as the Type R engine with single-stage supercharger. As the Air Ministry became aware of the project, they requested Supermarine to investigate adapting the Spitfire to accommodate the larger Griffin. Rolls-Royce was required to revise the Griffin to keep the length within the restraints of the Spitfire's limited space. Camshaft drives migrated to the front of the engine, as did the supercharger drive, both driven off the propeller reduction gearing. The magnetos were replaced by a single unit having electrical redundancy mounted above the propeller reduction case. Test versions of the Griffin II were running by June 1940. Development was delayed in 1940, as ordered by the Minister of Aircraft Production, to concentrate on advancing the Merlin production and development. When resumed, the production began with the 1,730 horsepower Griffin IIB for the Firefly and the Spitfire Mark 12. The later Griffin 61 introduced a two-stage supercharger with aftercooling rated at 2,035 horsepower at sea level and 1,850 horsepower at 21,000 feet for the Spitfire Mark 14. Improvements included a hollow crankshaft to deliver oil to the main and big end bearings directly. The Griffin 83 adopted a contra-rotating propeller gearbox and was rated at 2,340 horsepower, which became standard on late-model Seafire fighters. The final variants, the Griffin 3 series, including versions 101, 121, and 130, reached a zenith for Rolls-Royce V12 design, delivering 2,450 horsepower, a two-stage, three-speed supercharger, enhanced performance at low, medium, and high altitudes. Modular power package Griffin 57s were developed for the Avro Shackleton to replace their Merlins, allowing the same power to be developed at lower RPM, enhancing reliability and efficiency for long-range cruise operation. Production of the Griffin ceased in 1955, the last Rolls-Royce V12 aero engines produced. D. Napier and Son had established a reputation for building powerful liquid-cooled engines since the 1920s, with their Lion W12 engine powering several Supermarine Schneider trophy racers. They had also built the H-configured Rapier 16-cylinder and Dagger 24-cylinder air-cooled opposed engines during the mid-1930s. Work began in 1935 to design and build a larger H-configured liquid-cooled sleeve valve engine displacing 37 liters and making up to 2,000 horsepower. The Air Ministry supported Napier's project in 1937 as an alternative to other high-power engines still under development, should they fail to materialize. By 1938, Napier Sabre engines were passing test runs at 2,000 horsepower. Quality control issues in production slowed the pace of service entry, as did training of maintenance personnel in the differences of the unique engine arrangement. By 1944, the Sabre 5 could deliver up to 2,400 horsepower reliably in the Typhoon and Tempest fighters. Both were altitude rated and limited to combat at lower levels, but yet the Tempest was among the fastest RAF fighters and was employed to intercept V-1s. Nakajima's effort to surpass their Sakai 14-cylinder radial was the N9K Homura 21. The short-stroke 18-cylinder engine with 35-liter displacement was designed for compact installation. The close-fitting cylinders impaired quality in manufacture, hampering both introduction and service. Production began in 1941. Initial Homura 11s with two-speed single-stage superchargers delivered up to 1,900 horsepower. Many of the more capable late-war Japanese fighter designs, including the Kawanishi N1K2 Shidenkai, the Nakajima Ki-84, and the Yokosuka P1Y1 Francis, were powered by the Homura 21. What turned out to be a mere footnote in the story of successful high-power piston aero engine technology, Bristol's final radial engine, the Centaurus, could have been a game-changer but for the allocation of priorities that prevailed. Ambitious from the outset, the Centaurus pushed Bristol's previous design experience with the Hercules in every way. It increased the number of cylinders from 14 to 18. It increased the swept volume from 38 liters to 54 liters and did so with only a 6% increase in diameter by increasing the stroke from 6.5 to 7 inches. Given the advantages of the sleeve valve as applied to high power, this should have demanded a higher priority. Although conceived in 1938, the Centaurus did not enter production until 1942, while Bristol concentrated on production of the Hercules engine. In advancing the power density from the Hercules 1,500 horsepower to nearly 2,500 horsepower, one of the challenges was the cylinder head and sleeve metallurgy. Supercharger development handicapped the Centaurus as higher boosts were eventually applied to the engine. Sleeve valves suffered from warpage, proving difficult to cure. The engine was eventually produced to reliably reach its potential, but too late for combat in World War II. In service after World War II, through the Korean War, Hawker's superb development of the Tempest became the Fury and Sea Fury series. Integrating the high-powered Centaurus into the aerodynamically refined Hawker-designed airframe, the piston engine fighter reached its zenith of performance. Large piston engine fighters persisted for many years in naval service as the challenges of turbojet power were yet to be overcome. In 1937, the quest for larger increases in horsepower, especially as applied to large aircraft requiring increasingly longer ranges, pushed design norms toward the unconventional. The Army pressed Allison for a 2,000 horsepower engine at a time when development for their 1,000 horsepower V1710 was moving forward at a very slow pace. Benefiting from Allison's concept of modular engine construction for the V1710, the concept for the double V engine promised versatility and applications in any arrangement imaginable. Drives could be pusher, tractor, single shaft, dual shaft, or dual rotation shafts, remote extension, and handed rotation shafts. The two Vs were joined in a single crankcase oriented to each other at 90 degrees with independent crankshafts. Fate intervened in the V3420's journey from concept to existence. Ever-changing Army requirements, in addition to existing demand for V1710 resources, conspired to delay the prototypes. Delayed until March 1940, type tests began, only to be shuttered in the fall of 1940 as the need for V1710s became extreme. Early in 1941, recognizing the importance of their commitment to the Boeing B-29 Superfortress program, the Army returned to Allison for a 3,000 horsepower V3420 installation as a standby interchangeable program for the troubled Wright R-3350. The test bed for this was the Fisher-produced B-39 with close-coupled gearbox driving a single propeller and supercharged by a single larger two-stage GE turbo supercharger. While the Army waffled on the Allison V project, another design that could not seem to find its way was chosen as a candidate for the V3420. Fisher's large fighter project, the P-75 Eagle, originated as a quick-to-implement combination of already built airframe components using a never-built engine. As it evolved, it was built of entirely new and redesigned components, and would be the first to employ the Allison V3420B engine driving contra-rotating propellers. Redesignated XP-75A, the first Eagle was ready for flight in November 1943, after nearly 4 years in the making. Problems with the engine making full power were determined to be a result of dividing the supercharger flow between the two trunks to each V. This also served to renew Army interests to further pursue direct fuel injection for the Allison. By June 1944, the Army placed an order for 2,500 P-75A Eagle long-range escort fighters, which did enter production, and 14 were built. Allison further tested the two-stage intercooled V3420B-12 in the Eagle after the project was canceled, which delivered 3,150 horsepower at sea level and 3,050 horsepower at 18,000 feet. The Allison V1710 was the first engine to pass the 150-hour type test at 1,000 horsepower. The V3420 was the first engine to deliver 1 brake horsepower per pound and the first engine ever to pass the 150-hour type test at more than 2,000 horsepower. In contrast with the similar Allison concept V engine, the Daimler-Benz DB610 consisted of two mirror-image DB605 inverted V12s with independent crankcases joined by a common propeller reduction gear unit. The DB610 was preceded by a similar concept DB606 built from pairing two DB601s. Daimler-Benz discovered that with the inverted V12 arrangement, cylinders tended to accumulate oil in the bank opposite the supercharger. This led to early onset detonation at high power settings and was accommodated with reduced compression ratio for that bank. When coupling two V12s, the inner banks of the coupled engine sat in a vertical arrangement, further aggravating the condition. Inner cylinder banks also ran hotter due to their close proximity to each other, which further increased the likelihood of detonation. The single airframe produced for service with the Doppelmotor, the Heinkel HE-177, never did overcome these issues, frequently falling victim to engine fires and failure. Incremental improvements throughout the V1710E F series engines continued. achieving a state of equivalence with the latest Rolls-Royce Merlin RM14 SM engines. The V1710 F32R was specifically developed for the North American XP-51J. Changes included a 12 and 3/16 inch aux supercharger impeller, Bendix SD400 speed density computing fuel pump, and aftercooling to remove 50% heat of compression. It was rated at 3,200 RPM, delivering 1,900 horsepower at sea level and 1,725 horsepower at 21,000 feet. The last production version of the V1710 incorporated additional changes standardizing the 12 counterweight crankshaft and increasing engine stage supercharger impeller from 9.5 to 10.25 inches in diameter. The Bendix SD400 speed density computing fuel pump replaced the pressure carburetor measuring temperature, air density, throttle position, and RPM to determine fuel to be metered into the supercharger as an analog fuel control unit. The larger diameter aux supercharger had a larger inlet and a higher 8.08 to 1 step-up gear ratio to improve higher mass flow volumes to the engine stage. Displayed Allison supercharger impeller developments show this progression. On the left, F-Series engine stage impeller at 9.5 inches diameter. Middle, G-Series engine stage impeller at 10.25 inches diameter. And on the right, G-Series aux stage impeller at 12 and 3/16 inches diameter. A view of the step-up gear for the aux stage with impeller diffuser and general flow to the SD400 fuel metering pump just prior to the engine stage supercharger. Built specifically for the P-82 E, F, and G series fighters, Allison's V1710 G6 R and L were right and left-hand versions with military designation -134, 135. These engines could maintain 100 inches manifold pressure continuously and had a war emergency rating of 2,200 horsepower with water methanol injection. The profile view of the G6 indicates its increased length due to the aux stage supercharger. Propeller reduction gear ratio was increased to 2.36 to 1 to accommodate the 3,200 RPM rating at maximum power. The North American F-82 remained in service well into the transition to turbojet technology, as it was the only airplane capable of very long-range bomber escort. Radar-equipped F-82 F and G models carried out long-range air defense command patrols and intercept roles in North America and the Far East Air Forces. A Far East Air Force F-82G scored the first aerial kill of the Korean War against North Korean flight of LA-7 and Yak-9 fighters over Kimpo Airfield near Seoul, Korea on June 27, 1950. With the R-2800 investment coming into fruition, Pratt & Whitney's new chief engineer Luke Hobbs pursued a concept for a more powerful successor. Mega engines were abundant in proposal, but few met the challenge of providing practical service. He investigated the feasibility of a 4-row conventional air-cooled radial with promising results, and convinced Hap Arnold that it could be done. How do you bring 4,000 cubic inches into an arrangement that allows all the various pieces to function, while keeping size and weight manageable? Using previous experience and knowing the challenges, engineers Meade and Hobbs juxtaposed several possible arrangements and came up with the most feasible choice. 4 rows of 7 cylinders arranged in a helical twist offered positioning space for air to cool properly, exhaust to exit smoothly, induction to feed directly, and yet still be of a relatively standard diameter and size. Experience showed that the complexity of issues to resolve increased exponentially with displacement. From first design work beginning in the summer of 1940, Using plenty of existing components, a proof-of-concept engine was running by April 1941. 1 year later, a flight test engine was airborne, and production had begun by the fall of 1943. Pratt and Whitney instigated a proposal to Bureau of Aeronautics in early 1943 to install one of their R-4360 Wasp Major engines in a standard F4U-1 Corsair. A simple single-stage variable-speed supercharged version was chosen to eliminate complexity surrounding the installation. Although Goodyear was eventually selected to produce the Super Corsair, Pratt & Whitney carried out all of the engineering and retrofit work. The F-2G was beginning production when the war ended. Among the assets of the Wasp Major by design was its adaptability. As pioneered by the R2800 project, it was intended that the engine accommodate all manner of configurations to include supercharging and propeller arrangement. Boeing's massive fighter-bomber torpedo attack aircraft, the XF-8B, featured two-stage variable speed supercharging, contra-rotating propellers, and was designed from the outset to use the R-4360. The Cleveland Air Races resumed after World War II, and several of the Goodyear-built Super Corsairs were purchased as surplus, entered, and successfully competed. Owner Cook Cleveland, former naval aviator and Navy Cross recipient, sponsored 4 of the 5 F-2Gs built. Race 74 won the Thompson Trophy race in 1947. Race 94 won the 1949 Thompson Trophy race, and Race 57 won the 1949 Tinnerman Trophy race. The R-4360 powered Super Corsair concept resurfaced again in 1982 as a competitor in the Reno National Championship air races. Built by Jim Maloney and Steve Hinton's team at Plains of Fame Museum in Chino, California. Steve Hinton reported in an interview that the Bud Light Super Corsair was built from an airframe that had not flown since 1945, with a donated engine, a modified A-26 cowl, and a Skyraider propeller. The racer was built between May and August of 1982, in time for some testing prior to the 1982 Reno event. Hinton further stated that they had operated the engine for hours at 3,800 horsepower and that it was run at 4,150 horsepower during one race, winning the 1985 Reno Gold Championship at 438 miles per hour. The majority of the production of Wasp Major engines following World War II were operated in far less colorful surroundings. The workhorse R-4360-35 in the Boeing KB-50J delivered 3,500 horsepower for takeoff. These engines had a single aux-stage turbo supercharger with intercooling and were a common installation in both commercial Boeing 377 Stratocruisers and military C-97 and KC-97 derivatives. The ultimate in complexity of piston power, however, was the installation of the R-4360 in Combair's massive 6-engine B-36 Peacemaker. The adaptability of the design saw it installed within the wings in a pusher configuration, fan-cooled with parallel turbo supercharger systems. The B-36 was so large that it was considered underpowered with 6 engines capable of 3,500 horsepower each, so it was supplemented with an additional 4 J-47 engines adopted in the twin pod mounts from the Boeing B-47 Stratojet. Roots of the practical turbojet trace back to the engineering studies done in a thesis by Frank Whittle as an aircraft apprentice at RAF Cranwell. In 1930, Whittle took out a patent on his design, and further engineering study was undertaken at Cambridge University, where he graduated. Without government funding, he formed Powerjets Limited to build a prototype which was successfully demonstrated in 1937. Support for Powerjets came from British Thomson Houston, a subsidiary of General Electric UK, who provided shop space and qualified technicians. Later interest by Rolls-Royce afforded experimental shop services in manufacturing components. As work proceeded and the Air Ministry support materialized, a specification was issued for test aircraft, the Gloster E-28-39, to be powered by the Powerjet's W1 turbojet. The 850-pound thrust W1 was successfully tested in the Gloster test plane, with first flight taking place on May 15, 1941. Further development by Powerjets resulted in the W2 engine, which was eventually produced by Rolls-Royce as the 1,600-pound thrust Derwent, powering Britain's first operational jet fighter, the Gloster Meteor. The Meteor first flew on March 5, 1943. Design engineering and a Whittle W1 engine were shared with General Electric in 1941, where it was built as the Model IA. The production version of this engine received a designation of J31, and this powered the first experimental jet fighter produced in the United States, the Bell XP-59 Aerocomet, with first flight occurring in October 1942. The twin-engine P-59 was not a particularly ambitious design from an aerodynamic standpoint, and performance was less than impressive compared to propeller-driven fighters already in service. Bell completed 20 P-59As and 30 P-59Bs that were used by the Army Air Force to gain an understanding of the new technology, mostly in pilot training and maintenance squadrons. When intelligence revealed the existence of the Messerschmitt Me-262 test program in mid-1943, with some urgency, Hap Arnold directed Wright Field Materiel Command to contract with Lockheed to produce a fighter of comparable or better performance. Lockheed had conducted studies on turbojet-powered designs since 1939 based upon the Powerjet's demonstrated successes. Acknowledged to be the first true Skunk Works project, beginning June 26, 1943, Kelly Johnson's team produced the XP-80 airframe in 143 days, delivering it to the Army's Muroc Dry Lake test location in October of 1943. Some delays were incurred as the original de Havilland Goblin engine was damaged by FOD during initial tests. Test recommenced in January 1944, with pilot Milo Burcham making the first flight powered by the Halford H-1 engine. The Halford and Goblin engines were redesigns of the Whittle engine with straight-through flow from the compressor and burn cans to the turbine. The H-1 developed 2,300 pounds thrust, and the XP-80A demonstrated a top speed of 502 miles per hour in level flight. While it has been established that Frank Whittle's patented work on the turbojet design predated experiments begun in Germany, the results of Hans von Ohein's pioneering work were translated by Ernst Heinkel's engineering team into a viable test engine, the HES-1. Heinkel Strahl Triebwerk translates Heinkel jet engine. Refinement of the design resulted in the HES-3 flightworthy engine, which was successfully test-flown in August 1939 in the world's first turbojet-powered aircraft, the Heinkel HE-178. Given the task to develop a production turbojet for military aircraft, Dr. Anselm Franz of Junkers Motorenwerk applied new research from the AVA, Aerodynamic Research Institute, in Göttingen. An axial flow compressor was selected for lower cross-section and its direct flow characteristics. Simplifying the engine in the interests of expediting tests, the thrust of the resulting UMO 004A was well below its potential at 950 pounds thrust. First bench tested in October 1940 with compressor stator vibration issues solved, the 004A passed a 10-hour endurance test at 2,200 pounds thrust in December 1941. The initial flight test was made mounted below the fuselage of a Bf-110 test bed in March 1942. Summarizing the design, it featured an 8-stage axial flow compressor with 6 individual straight-through flow combustion chambers and a 1-stage power turbine with hollow steel blades. Messerschmitt's initial design program for a turbojet-powered fighter designated P-1065 began in April 1939 with a plan to use BMW's projected 003 turbojet engines. Similar to the Gloucester Meteor, it was intended to power the ME-262 with 2 turbojets to ensure sufficient thrust to meet design requirements. Flight testing of the ME-262 began in April 1941 with 2 BMW 003 engines and a UMO 210 piston engine mounted in the nose. Both BMW 003 engines failed on the first test, and power was changed to UMO 004A engines, which showed more development progress. The first purely turbojet flight occurred on July 18, 1942, piloted by Messerschmitt flight test pilot Fritz Wendel, 9 months prior to the first flight of the Gloucester Meteor. The first 4 prototypes were built with a conventional tailwheel, but on its first flight, Wendel discovered that the elevator was blanked by turbulence of the wing and engine thrust, rendering pitch control useless on takeoff. Cleverly tapping the brakes, the prototype pitched nose down to allow normal acceleration to take off speed. One critical design feature of the ME-262 was its slight wing sweep. Initial drawings with the P-1065 featured a typical straight wing, but as the BMW 003 turbojets projected heavier than planned, the wings were adjusted to have a mild sweep back to maintain the proper center of gravity projection. As it was later studied, this sweep gave the ME-262 a higher than planned critical Mach number, even though it was not the reason for employing it. The world's first production-built turbojet-powered fighter, however, was not without its difficulties, as the nascent turbojet engines proved troublesome in service, requiring specialized pilot training in their operation. Typically, slow acceleration and metallurgical deficiencies caused frequent failures and losses. UMO 004B engines were the final production variant for the ME-262, redesigned to use available metallurgy because of shortages of high-temperature alloys of nickel, cobalt, and molybdenum. The overhaul interval was reduced to 25 hours with additional 10 hours if inspection warranted it. 35 hours was the maximum allowable interval. Another development in propulsion that was more actively pursued in Germany was that of liquid-fueled rocket motors. Helmuth Walter's HWK firm teamed up with Ernst Haeckel to build a series of liquid propellant rocket motors, including a more stable Z-Stoff-powered or cold R2-203 engine, which powered early ME-163A prototypes. In October 1941, the ME-163A V4 prototype took off from the Baltic Coast Test Base at Peenemünde, setting a new world speed record of 624 miles per hour, piloted by Heine Dittmar. 10 ME-163A prototypes were built for further testing and pilot training. The R2-203 engine could not be throttled and was simply switched off during the climb to control excess speed and extend endurance. By 1941, work had commenced on a new bifuel hot rocket motor, the HWK 509 series. The HWK-509A was designed to meet the requirement to be throttleable. To accomplish this, a combination of two fuels, C-STOF and T-STOF, were to be injected into a combustion chamber by means of separate turbopumps, whereby the reaction would release enormous energy to be vented by a thrust nozzle. A new production version of the aircraft, the Me-163B Comet, was produced by Alexander Lippisch in coordination with Messerschmitt AG to use the new engine and develop its combat usefulness. The throttle in the 509A version was found to be so inefficient it did not prolong the endurance of the Comet. A new version, the HWK-509B, was then in development to solve the problem. The HWK-509B was designed with two separate combustion chambers, one with a smaller, lower output chamber directly below the main chamber. In this way, thrust would be reduced from 4,000 pounds thrust to 220 pounds thrust, allowing a significant reduction in fuel consumption. Lippisch's tailless design confirmed his long-standing work with unconventional and unpowered designs. The Comet was known for its very docile handling characteristics. However, these were offset to a large degree by the volatile nature of the highly corrosive fuels. A bounced or heavy landing exposed the pilot to lethal hazards of these fuels on more than one occasion. Heine Dittmar's record of 624 miles per hour stood until after the war had ended, when surpassed by the Douglas D-558 turbojet-powered research plane in August of 1947. In a matter of months, the records began to tumble readily as high-speed research aircraft routinely probed the limits of both aero and thermodynamics. These test programs not only investigated the limits of aerodynamics, but also the requirements for advanced materials to withstand flight at extreme speeds and altitudes. Tests were conducted at altitudes of more than 100 kilometers and a maximum speed of greater than 4,500 miles per hour. The use of reaction motors to adjust attitude and flight path were precursors to flight beyond the stratosphere. We have witnessed in this series some of the highlights of the development of air power in the first half of the 20th century. Piston aero engine output from levels below 100 horsepower reached upwards of 4,000 horsepower in less than 3 decades' time. New and seemingly unlimited levels of power and performance loomed upon the horizon as we entered the jet age. The first steps were being taken to demonstrate controlled flight and practical navigation beyond the stratosphere, with the possibility of future spaceflight clearly within our grasp.